Hello, this is the third part of our lectures on quantum mechanics of applied physics UPS 004. In the previous two lectures on quantum mechanics, we have learned about the necessity of quantum mechanics in solving the problems of microscopic world. Some crises were discussed with classical mechanics. Then we have learned about fundamental principles the quantum mechanics is based upon. And after having informed about those fundamental principles on which the quantum mechanics depends, we are at the stage to understand the postulates of quantum mechanics. These postulates are the method to solve the problems, or in other words, these make the model of quantum mechanics. Before proceeding further, we have to keep in our minds that it is not necessary that these postulates will show any physical aspect, because these are entirely mathematical concepts which are developed one by one in order to formulate quantum mechanical method to solve any problem. The only physical significance of these postulates is that they have an exact solution of real world questions, or in other words, the predictions using the systematic quantum mechanical postulates match exactly with the observations. So, first postulate of quantum mechanics is the concept of wave function. It states that any state of a physical system can be represented by a mathematical wave function that contains all the information about the system. This wave function is represented by psi as a function of position and time. This is an example of mathematical wave function of moving particle, of course in graphical form. Like what you have already studied in wave group, that a particle is represented by wave group made up of superposition of many matter waves giving constructive and destructive interference in the different region of space and time. Here we go one step further by saying if there is a particle system in space, then the group of matter waves superpose with each other in such a way that there is a constructive interference in region where there is a probability of existence of particle, and the matter wave interfere destructively in all the other regions where there is zero probability of particles presence. If somebody asks about physical significance of wave function, then it has no physical significance, but its square does have. The square of wave function represents the probability of finding a particle in a specific region of space. So, if psi is the wave function, this, then integral of its square from r1 to r2 is the probability of finding this particle in region from r1 to r2. A wave function may have any form of mathematical function ranging from real to complex variables or trigonometrical to exponential functions. The only condition is that it must follow few essential characteristics. These characteristics are as follows. A wave function of a real physical system must be single valued, as the particle in real world cannot be found at two places simultaneously. And secondly, a wave function must converge or vanish at infinity. This condition ensures that a particle can be found in a certain region of space only. And next, the derivatives of a wave function must be continuous. This condition can assure that the probability of particles' existence does not change abruptly, as in nature nothing happens suddenly. Along with the above necessary characteristics of an acceptable wave function, another condition is required for quantitative results, and it is known as normalization condition. It states that the total probability of finding particle in all the space of the world must be unity, as probability cannot be greater than 1. Let us have few examples. Here, few wave functions are represented in graphical form. In the uppermost, this wave function indeed vanishes at infinity. It is single valued, it is continuous also, but its derivative is not continuous, at this point. So it cannot be an acceptable wave function. In the second wave function, this vanishes at infinity, right? It is single valued at every point of x-axis, right? It is continuous and its derivative is also continuous. So it is indeed an acceptable wave function. And the third wave function is not continuous, so it cannot be an acceptable wave function. In these cases also, it can be easily found that the above wave function this is acceptable and this is not. So in these examples, these two wave functions are acceptable. Once a wave function is in place containing all the information about the system, the question is how to extract that information. The tool which does it is called an operator. The observable O in classical mechanics is replaced by an operator O cap in quantum mechanics. According to correspondence principle, for every physical quantity one can define an operator, and the definition takes help from the formula in classical physics. So the quantum mechanics is built from classical physics in spite of altering its limits. Now, what is operator? There are some set of instructions which, when applied to the wave function, give the desired value of the observable in quantum mechanics. These set of instructions are known as operator. For each observable, there are unique instructions. An operator is represented by a cap over it. Let us have an example. The simplest example of wave function can be the wave function of a moving free particle. It has a wave equation psi xt is equal to a exponential iota kx minus omega t. It is same as sine kx minus omega t or cos kx minus omega t, where k is wave propagation vector and this is given by 2 pi by lambda, where lambda is h upon b by de Broglie hypothesis and omega is angular frequency 2 pi nu, where nu is e by h by Planck's hypothesis. So the substitution can simplify this equation as this, where P is the momentum of the particle and E is the total energy of the particle. Now we need some instructions to find the value of this P and E. To extract this P out of this equation, we need to differentiate this equation with respect to position. So if we do that, we get this, or we can rewrite this equation like this. This P can be written as P cap, where P cap is operator. It is because P multiplied by psi is equal to this operator or set of instructions applied to the wave function. So by this we can conclude that the momentum operator is equivalent to this instruction. Similarly, the energy can be found by differentiation with respect to t, and the energy operator can be written like this. So these are momentum operator and energy operator. Although these are found using a free particle, but in quantum mechanics these are applicable everywhere. This is the total energy operator in quantum mechanics. In classical physics, the total energy is known as Hamiltonian, which is the summation of kinetic energy and potential energy. So total energy operator can be found in other way also. For that, we will have to find the operator for kinetic energy, which is px square by 2m, or the kinetic energy operator will be this. There is no specific potential energy operator, but mostly the potential energy operator is a function of x. So the Hamiltonian of a system is the summation of kinetic energy and potential energy. Similarly, Hamiltonian operator in quantum mechanics can be written as summation of kinetic energy operator and potential energy operator along x-axis, and in 3D it can be written like this. So this is Hamiltonian operator in quantum mechanics. These are few more operators, like for position operator, we put only X in quantum mechanics, this is linear momentum operator, or P, this is potential energy operator, kinetic energy operator, total energy operator, and Hamiltonian operator. The third postulate tells about the experiment. If you have a wave function and an operator corresponding to a desired observable, then too it is not necessary that the given operator gives an acceptable value of the observable after acting on the wave function. But it will do so if after operated by the operator the wave function remains unaffected and it gets a number as a multiplier. It is because, as you know, the state of system is represented by the wave function. If you perform the measurement and this experiment leads to the change of the system itself, then there is no meaning of the experiment. It is similar that there is no meaning of telling about the condition of a bone of a person if you kill that person to do so. This postulate is known as postulate of eigenvalue equation. When an operator is operated on a wave function and it gives the same wave function multiplied by some number, then for this operator, this wave function is known as eigenfunction of the operator. And this value is known as eigenvalue for the operator. And this whole equation is known as eigenvalue equation. So for the real measurements, we need eigenvalue equation. The pair of wave function and operator which do not follow the eigenvalue equation are useless for us. The eigenvalue equation is equivalent to an experiment in laboratory. But merely performing an experiment is not enough in practice. You must have noticed that if you perform an experiment in laboratory in number of times, then no matter how precise it is, it gives different results each time. Now what you do to find the result? You take the average of all the values found by different experiments. In quantum mechanics, the method of taking average is different than that in classical mechanics. The average in quantum mechanics is known as an expectation value of the operator, and the method is this. The expectation value of the operator is represented by this, and it is given by this formula where psi star is complex conjugate of the wave function. This formula is for normalized wave function. If this wave function is not normalized, then we shall use this formula. Now comes the fifth postulate of Schrödinger equation. This equation enables us to find the wave function of a real system, and it also tells about how the wave function evolves in space and time. Strictly speaking, there is no abstract derivation of Schrödinger equation, like there is no derivation of Newton's law of motion. There are two forms of Schrödinger equation. One is time-dependent form and another is time-independent form. I shall try to give a method to find it, or more truly, the method to remember it. So get ready for some mathematical exercises now. Let us start with time-dependent Schrödinger equation. You must have noticed that to compute the total energy of the system, there are two operators. One is total energy operator and another is Hamiltonian operator. It can be said mathematically like this. Hamiltonian operator operated on the wave function and total energy operator operated on the same wave function give the same value. If you put corresponding instructions or the value of these operators here, we get this thing along one dimension. And in three-dimensional system, this will be like that, or like this, where this is the Laplacian of the system. These equations, this and this, are known as time-dependent Schrödinger equation. So the method is very simple to remember h psi equal to E psi and then put the value of Hamiltonian operator and total energy operator. Time-independent Schrödinger equation can also be found by time-dependent Schrödinger equation, and for this we shall use the method of separation of variables. It means if there are two variables, we can separate them out. Like the wave function is the function of the position and time both. If we can separate this whole function, mathematical function, in product of two functions which are the functions of position only and the time only, then we can omit the time dependence from the Schrodinger equation. But the question arises that is it always possible to separate the variables? The answer to this question is not universal, but for most of the systems it is possible. It is so because most of the forces are either not changing with time, or we are interested in the events so rapid that the time involvement can be avoided. So if you put this wave function in time dependent Schrodinger equation here, then it will be like this. Now we can simplify this equation and it becomes like this. Here this u is the potential energy operator and this is the function of position only for most of the cases. So if you look at this equation, you will notice that the left hand side is the function of position only, while the right hand side is the function of time only. Still, both the sides are equal. How is it possible? It is possible only if both the sides are equal to a constant. Let that constant is E. We'll call it a separation constant. Now we can have two equations. One this and another this. This is position dependent and this is time dependent. Let us solve this equation first. We can simplify this like that and we can solve it to have phi t is equal to exponential minus iota e t divided by h bar. So this is the time evolution of the wave function. Now we come to this equation. This can be simplified like this. Here this is potential energy operator operated on the wave function, and in quantum mechanics the wave functions which are not the eigenfunctions are useless. So this must be the eigenfunction of this operator, and this can be written like this. The potential energy operator operated on the eigenfunction gives the value of potential energy multiplied by the wave function. So it can be replaced by this. So it becomes like this, or it can be simplified like this, known as time independent Schrodinger equation, and this gives the time evolution of the wave function. So this is time dependent Schrodinger equation, where this is the total energy term, this is kinetic energy term, and this is potential energy term. When we apply the method of separation of variables, which means we write the wave function as a function of position and time equal to the solution for time evolution multiplied by the wave function dependent upon position only, then we get the time independent Schrodinger equation. We will use in most of the times this time independent Schrodinger equation. In the next lectures, we will discuss some applications of quantum mechanics, and few of these applications are the particle trapped in one-dimensional potential box, particle encountering a potential barrier, and quantum mechanical tunneling.